All right, welcome back. We are still on homework number 1. This is problem number 4, and homework 1 is on Maxwell's relationships. Okay. So, number 4. Show internal energy of an ideal gas is only a function of temperature using at least 2 derivatives. Okay. So this is a numeracy. This is a Maxwell's relationship. But this is also a numeracy question. I have to read the problem. All right. So let's read the problem very carefully. Okay, it says an ideal gas. Okay, what is ideal gas? That's an equation of state. Okay, so that has to do with step 5. We're not there yet. Okay, so ideal gas, we'll keep that in our mind, but not yet. Okay, so show internal energy. Well, I know what that is. U is only a function of temperature. Using at least 2 derivatives. Okay, so I'm going to have d something at constant something. Okay. All right. Well, which one's the independent? Which one's the dependent? Okay. Yeah, use the dependent, so it's going to be on top. Yeah. Now, where do I put that t? I have 2 choices. I can either put it here, or I can put it here. Which one do I put it on? Well, let's look what it says. Show internal energy is only a function of temperature. So, let's think about f of x and y equaling. So let's say I have, let's say I have a second variable here, like, I don't know, b. Okay. So I've got f of x and y, or u, t, and b. But if f is only a function of x and y, well, a good example would be this guy. Right? Okay. So, assuming x has no relationship to y. Okay, assuming d, Okay, so if I took, let's say I have f of x of y, and it's only, I can see that is only a function of x, right? Okay, so I have 2 choices. I can either do df dx at constant y, or df dy at constant x. Let's do that. df dx constant y is going to equal 2x, right? Yeah, because y was kept constant, right? Well, it might be like, well, why do you keep y constant? There is no y. Exactly. Because what if I take the derivative of that with respect to y, keeping x constant? You'd be like, okay, but how does that tell me that it's only a function of y? Well, let's think about what that derivative says and what I'm trying to show. I'm saying it's a function. I'm saying u is only a function of t, meaning the relationship, the only relationship that has meaning is du dt. It's the only relationship that has meaning. Right? It's the only relationship that has meaning because it's only a function of temperature. All right, but let's go back to our numeracy. What does this say? How does u changes in t? Meaning, what? U will only change with changes in t. If it's only a function of temperature, it's only going to change with t. So, how do I show, how do I give an example of it being only a function of t? Because if I did that, let's just say I did this. Because we all know what that is. Du dt at constant b, that's equal to cv. Well, we all know that heat capacity, well, that's only a function of temperature for an ideal gas. We're done, right? Well, why is heat capacity only a function of temperature for an ideal gas? Because internal energy is only a function of temperature for an ideal gas. That's a circular argument there. That's like saying, oh, well, the Earth is round because, well, if it, because the round thing said it was the Earth, or whatever. That was a really bad example, but you get my point. CV is only a function of temperature because U is only a function of temperature, and because of that relationship. All right, so that doesn't help us. That doesn't say anything. But if I kept T constant, how would U change? Assuming it only can change with T. It wouldn't. And what does wouldn't mean? What are the words for wouldn't? 0. And I can put anything in here. I can put in V, I can put in G if I wanted. So let's do something simple like V, and let's do something goofy like, well, let's do A. I like A better. So let's do dVu dV at constant T and see what happens for an ideal gas. But I really have to think about that. U is only a function of temperature, meaning that if I change anything else, let me rephrase that. Well, yeah, if I change anything else, but if I keep the one thing it depends upon constant, it can't change, because it's the only thing it depends upon. Okay. Think about a relationship. If I only depend upon my parents, and I shoot the president, am I going to be changed? No, because I only depend upon my parents. Now, if I shoot my parents, then yes. All right, so that's my numeracy. The rest is Maxwell's. So, do I have a funky function? Nope. What's my next question? Do I have an HTC in the constants place? Nope. Next question. Do I have an HTC in the D place? Yep. I have a U. Okay. Sub question. Is it on top? Yes, it is. Okay. If it's not on top, remember you have to do the inverse, and do not forget to re-inverse it when you're all done. Okay. But yes, so it is on top. I'm good to go. I see a DU. What do? I plug it in. So, plug it in. du is equal to TdS minus PdV. That's the one I should just have memorized. I plug it in, and so I have this guy is equal to T ds dv at constant t minus P dv dv at constant t. And that's why I choose V. That goes to 1. Well, that doesn't do anything yet. Okay. Alright, so that goes to 1. Alright, so do I still have an HTC in the D place? Nope. Okay, next question. Do I have an S in the constants place? Nope. Okay, next question. Do I have a DS? Yes, I do. I have a DS right here. Okay. So I have 2 choices with the DS. What are my 2 choices? I can either, that's right, use Maxwell's relationship. So let's look. Now, most likely, if there's a DS, there probably is a Maxwell relationship. Okay, so I go and I find ds dv at constant t. Yep, it's right there. Does it get rid of the S? Yep. Okay, then that's the one I do. If it does not get rid of the S, then I use the chain rule. All right. But I don't have to in this case. So this is equal to T dP dt at constant V minus P. All right. Do I have a ds? Nope. Okay. Do I want measurables, properties, or an equation of state? You want an equation of state, Dr. Heavy? They're right. That's what. I have an audience member right now. So, I want an equation of state. So, should I change that dP dt at constant V to a beta over kappa? No! I just take the derivative. So P is equal to RT over V. Okay, dP dt at constant V. Well, that's just R over V. Right. So RT over V, which is also equal to P minus P. Well, what's P minus P? Oh, it's 0. Spooky. Okay. That's going to happen every single time. But you know, I did promise you 2, so let's do something goofy like du dA. Okay? So I have du dA at constant t. Well, this becomes 0, yes, it will be simple. Okay. So, same questions though. Do I have a funky function? No, I do not. Do I have an HTC in the constants place? No, I do not. Do I have an HTC in the D place? Yes, I do. Is it on top? It's on both. What do? Well, do the one on top and then do the one on the bottom. Okay, so T ds dA at constant t minus P dV dA at constant t. And I ask myself the same question: do I have a HTC in the dx place? Yes, I do. Is it on top? No, it's not. So I have to inverse it. Okay, so let's do each one separately and then inverse it. Okay, so yeah, first I have dA ds at constant t. What do I do when I have a dA? Plug it in. Where'd that lid go? Okay. Well, I'm going to have fun with this. Minus s dt ds at constant t minus p dv ds at constant t. Oh, well, that's equal to 0 because it's constant t. All right. And so I have that, and so the inverse is going to be minus ds dv at constant t divided by p. Okay? But we'll mess with that one later. So dA dV at constant t is equal to minus s dt dV at constant t. Oh, that's also equal to 0. Minus p dV at constant t. Well, that's equal to 1. So all I have left is minus p, but it's going to be inverse, so it's going to be minus 1 over p. Okay. So when I plug them all back in, I get this guy is equal to minus t over p ds dv at constant t minus p over minus p. Plus 1. Now, does that make sense? I mean, it doesn't have anything. It means it doesn't have any units. Let's look at step, if we kind of look ahead to step 6, check your units. Does that make sense? Well, what's the units of energy? What's the units of Helmholtz free energy? They're the same, so it should be unitless when it's all said and done. What about that other one? Is that unitless? Well, I mean, yes, it is. I'll say it is, but it's hard to tell right now, so let's just leave it as B and wait till step 6 to see, to confirm it is unitless. Okay, so do I have an HTC in the dx place? No, I don't. Do I have a S in the constants place? No, I don't. Do I have, survey says, a ds? Yes, I do. Okay, so I have a ds. What do I do when I have a ds? Well, I think that's actually the same exact ds I had last time, but it doesn't matter. You do the same questions every single time and say, hey, I have a ds. Do I have a Maxwell's relationship that gets rid of my s? Yes, I do. Plug it in. Okay. So, minus t over p d p dt at constant v. Oh, well, now I can see that they cancel out because I got p, t, t, and they all cancel out, and they're all going to be unitless, and everybody's going to be really happy. Okay, plus 1. Alright. Do I have a ds? Do I have properties, measurables, or any equation of state? That's That's right, I have an equation of state. It's called the ideal gas law. And so I take dP at constant V, with P being equal to RT over V. dP at constant V, same thing as before, is R over V. Plug that guy in, and I have minus RT over PV plus 1. Well, last time I checked, RT over PV is 1 for an ideal gas. 1 minus 1 is equal to 0. And that's all it is. Okay. But moral of the story is this guy. If you want to show that it's only a function of the variable, keep that one variable constant and see how the other one changes. Because again, it's all about relationships.